Hey guys, in this video we're going to talk by way of review about simple harmonic motion that you should have learned about in a previous video, and then pendulum motion, both for what are called simple pendulums and physical pendulums. All right, so to begin with, simple harmonic motion is any scenario where the acceleration is directly proportional to the position of the object and also is directed towards the equilibrium position. Conceptually, that includes things like, a spring, where it's, oscillating back and forth over some equilibrium position. It would also include something like a pendulum, where, right, ultimately it wants to get back to the equilibrium position, which is just hanging straight down, and it's constantly oscillating back and forth over that same territory. Mathematically, what it looks like for something to be in simple harmonic motion, though, is this expression here. So anytime the AP exam asks you to prove simple harmonic motion, you need to make something that looks like this. All right, whatever the scenario, turn it into this. The simplest case is where it's a spring, and this should be review, right? Where you have, all right, spring force equals the force, so mass times acceleration. Notice here, I know I didn't label it, but I'm starting with forces. You're always either going to start with forces or with torque for any kind of a proved simple harmonic motion scenario. Okay, so with forces, slight rearrangement and substituting in that acceleration is the second derivative of position, we get this. And at that point, you're actually done, because all you're going to say is this stuff in between the negative sign and the x is omega squared. And now it fits with that one right there. Okay, that's always how it's going to work. Whatever the thing is in between the negative sign and the position, whatever kind of position you're talking about, whether it's linear or angular, whatever this thing is, that's omega squared. Not omega, but omega squared. Okay, other things which are going to universally apply to any sort of oscillating scenario, the period of oscillation is 2 pi over omega for simple harmonic motion, where omega is, the square root of the whatever the thing was. All right, and then sort of final thought on springs. We showed before that this is the position function, and the way that we got there is by saying, look, it works, because if I take the derivative twice to get to the acceleration function, the acceleration is negative omega squared x. That's this statement right here. Okay, so all those pieces then fit together for our simple harmonic motion for a spring. But how do we prove that for pendulum motion? Okay, so what is going on with, that is analogous in a pendulum to what is going on in a spring? It's not perfectly analogous, and actually we'll discover that there's a point where pendulums break down and don't do simple harmonic motion. But as long as we stay sort of within certain parameters, it works and does demonstrate simple harmonic motion. All right, now we're going to begin, we said, with forces. That's where we start with springs. That's where we start with the simple pendulum. When we're talking about the forces on the pendulum, we should remember from way back in early mechanics that there's tension, there's the force of gravity acting on it. And also that because it's going on, some kind of an arc like this, we can't just talk about the horizontal forces, because, if you've ever watched a pendulum oscillate back and forth, it doesn't just move sideways, right? At any given moment, it's moving perpendicular to the string. So we have to, instead of talking about just x and y, talk about along a tilted axis. Okay, so we're going to introduce here a tilted axis, right? Perpendicular to the string. I hope that line's perpendicular. Okay. Now, for a tilted axis, the, quote, x direction is this way, parallel to motion. Oops, I didn't want red. And you should remember that the component of gravity, which is parallel to motion, is given by mg sine theta. All right, now I am not in this video going to get into where that is coming from. You need to go way back to understand why it's mg sine theta. Just take that as a given. Mg sine theta is the component of gravity parallel to motion. All right, and that equals ma. For pendulum motion, it's angular though, okay? It's not actually that helpful to talk about linear stuff because it's not just moving back and forth in a linear sense, it's actually moving along a circular arc. So instead of talking about linear acceleration, we are going to talk about angular acceleration. Okay, so also kind of going way back, A is alpha r from way back in the rotation unit. Okay, so if A is alpha r, I can sub that in. Oh, notice the mass cancels out. We'll talk about that more later. Okay, and then we have just g sine theta left on the left side here. Okay, now we have not a hope of making this look like simple harmonic motion unless we next do one very important voodoo calculus trick, and that is this. We have to use something called the small angle approximation. Here is the small angle approximation. Sine theta is equal to theta. Yeah, definitely works. Okay, no, that's not even kind of true. If I take sine of, we're in radians here, sine of pi over 2, that would equal 1, and pi over 2 is not 1. Last time I checked, Mr. Errico. Well, okay, so just bear with me. If I make a graph of sine theta, it's one of these deals. If I make a graph of y equals x on whatever wonky scale I've got here, there is a region where they are in relatively close agreement, and then they rapidly diverge and don't look anything similar. But as long as theta is small, like less than 10 degrees, maybe 15 degrees, it works, okay? Again, in radians. I don't know what 10 degrees is in radians, okay? But it works as long as theta is small, okay? You can try it if you like. Go ahead and type in sine of 0.1. Make sure you're in radian mode. And you should get like about 0.1. Okay, it's like 0.099, all right? So, but it's basically 0.1. And if we can say that sine of theta is basically equal to theta, that allows us to do something up here, which is just make it say g theta equals alpha r. All right, next. Alpha is the second derivative of theta. G over r theta equals this thing. All right, this is like so close to being right. Close, okay? A problem coming over here is the lack of a negative sign. Just being real, guys. If you're like, oh, crap, I need a negative sign. Close your eyes. There's a negative sign there. Don't even worry about how it happened. Now, that's not a very satisfying answer, so there's a few ways that you can get at it. One is you could argue that you should have put in a negative sign way the heck up here, because the direction of the acceleration was towards the equilibrium position, right? Not away from it, but towards it. So you could define that, this way as the negative direction because it's towards the equilibrium position. All right, or you could throw it in up here because you could say the angular acceleration is always going to be such that it's going to cause a decrease in the angular displacement. Somehow, somewhere, you need a negative sign or you won't be technically demonstrating simple harmonic motion. So supply the negative. It just happens and you put it in there. However you want to think about the fact that it belongs, you need to have it in there. Okay, and then this is of the correct form. All right, the only thing that's a little bit ambiguous here is what do I mean by R? And actually, most of the time they won't use R. They'll use L for a simple pendulum. Now it's maybe a little more obvious what L or R is. It's the length of the string, right? There it is. It's the length of the string. Well, okay, we have to be a little bit careful here. L is not really the length of the string for a simple pendulum. It's the distance between the pivot point and the center of mass of the system. Also, for this to be a simple pendulum, the string has to be of negligible mass, and the dimensions of the object have to be negligible in comparison to the length of the string. So if you can make those two assumptions, then you have a simple pendulum, and you don't have to do all the fuss and bother that's involved with doing a physical pendulum, which is our next thing. All right, so understand then that L is the distance from the pivot to the center of mass, and you're good to go. This allows you to get out of problems like, wait, what if the mass is like really long? Like one's a bigger mass than the other, right? The dimensions of it don't necessarily matter, you have to think about is from the pivot to the center of mass of that object. Okay, now notice things that are conspicuously absent here. Oh, excuse me. This is omega, so omega squared is g over, call it L. So therefore, the period of your simple pendulum is 2 pi over omega, and therefore 2 pi times root L over g. So things that are conspicuously absent, the mass of the pendulum bob. I would think that would matter, right? Like if I put a heavier thing there, isn't that going to be more difficult to make it oscillate? Well, our math says no. The mass canceled out way up here. And there is a point at which the dimensions of the object begin to matter. But the mass of the object in any direct sense is actually irrelevant. Okay, the mass never mattered. All right, so to demonstrate that, I actually have a little pendulum set up over here. You'll have to pardon the crowded table. Yeah, there's lots of stuff there. Okay, but can you even see the two objects? Yeah, I think they're visible enough. All right, so we've got a little weight and a big weight, and we're just going to do this. We're going to oscillate them. Those periods look awfully similar to me. The masses that I used were, let's see, one was basically a kilogram and one was 200 grams. So they were different by a factor of 5, and the periods are negligibly different. So negligibly different periods, even though the masses are not negligibly different, I set it up in such a way that the distance from the pivot to the center of mass was basically as close as I could get to the same for both objects, and therefore they will end up with having the same exact period. Okay, the other thing to mention about simple pendulum motion is the independence from amplitude. Springs are perfectly independent from amplitude as long as it's a linear spring. The period of oscillation for a simple pendulum is independent of amplitude as long as the small angle approximation holds, right? If that is not a good approximation, then it stops being independent of amplitude, okay? But if you have an oscillation over a 5-degree angle versus a 10-degree angle versus even like a 15-degree angle, the periods are all negligibly different over those small angular displacements. All right, next up is the physical pendulum.